In this video, we will derive an expression for the electrostatic potential energy in a given electrostatic situation. Until now, we have been interested in the potential difference or the potential. We have not considered in detail the electrostatic potential energy. So now let us do that. Let us say that there is this point point charge Q1 which is already present at this point. Now we bring a charge Q2 from infinity to, let us say, this point 2. Okay, so this charge is Q2. So the work done to bring this charge Q2 from infinity here will be equal to, what is the potential at this point? It will be Q1 over 4 pi epsilon naught R12. If this is R12, so this will be the potential, and potential is actually work done per unit charge. So you see, the work done will be the charge into the potential. So W2 is equal to Q2 into the potential at point 2. Similarly, I could have done other way, that I could have already kept Q2 here, and I will bring Q1 charge from infinity to this point. This is Q1, and again this is R12. So in this way, the work done will be same. It will be Q1 charge into the potential at this point. It is Q2 over 4 pi epsilon naught R12. So this is the potential at point 1. So from these two, we can see that these both work done are same because the configuration is same. So you see, if I add these two equations, so twice of W2 is equal to Q2 into V2 plus Q1 into V at point 1. So W2 is equal to half of Q2 into potential at point 2 plus Q1 into potential at point 1. Now let us bring another charge. So already Q1 is here, Q2 is here. Now I will bring Q3 charge from infinity. So let us say I have got it here. So this is R13, this is R23. So the additional work which I will have to do will be the charge into the potential there. And what will be the potential there? Q3 into the potential due to Q2 4 pi epsilon naught R23 plus potential due to the charge Q1 4 pi epsilon naught R13. So you see, the additional work done will be Q3 Q2 4 pi epsilon naught R23 plus Q3 Q1 4 pi epsilon naught R13. So the total work done will be W3 equal to W2 plus delta W equals to Q1 Q2 4 pi epsilon naught R12 plus Q1 Q3 4 pi epsilon naught R13 plus Q2 Q3 4 pi epsilon naught R23. Now I can write it again as 1 by 2 of Q1 V1 plus Q2 V2 plus Q3 V3. How I can do it? Let us see how. So potential at 1 will be potential due to charge 2 4 pi epsilon naught R12, and potential due to charge 3 4 pi epsilon naught R13. Similarly, potential at 2 will be potential due to charge 1 4 pi epsilon naught R12, and Q3 4 pi epsilon naught R23, and potential at 3 will be Q1 4 pi epsilon naught R13, and due to charge 2 will be 4 pi epsilon naught R23. So putting these values of V1, V2 and V3 here, I can write it simply as W3 is equal to 1 by 2 Q1 Q2 4 pi epsilon naught R12 plus Q1 Q3 4 pi epsilon naught R13 plus Q2 V2 is equal to Q2 Q1 4 pi epsilon naught R12 Q2 Q3 4 pi epsilon naught R23 plus Q3 Q1 4 pi epsilon naught R13 plus Q3 Q2 4 pi epsilon naught R23. Now from this expression you can see that there is this duplicacy, like this is coming double time, this is again coming double time, and this is again coming twice. So it is actually equal to q1 q2 4 pi epsilon naught r12 plus q1 q3 4 pi epsilon naught r13 plus q3 q2 4 pi epsilon naught r23. And this equation is same as the equation which we derived from the basic principle. So you see that we can generalize that the potential energy, just a minute, something has happened. Yes, something had happened to the pen tab. Let us continue. Now you can see that we can generalize that potential energy due to a combination of various charges q1, q2, q3 up to qn can be generalized as the total work done or the potential energy stored is half of qk vk, where k is varying from 1 to n. So this is one of the most important expression which we will use in deriving the potential energy of various configuration. Now in the next slide we will try to use this equation to calculate or solve a numerical example. So let us see what is the numerical example. We want to calculate the energy required to assemble a sphere with uniform volume charge density given by rho, and the radius of this sphere is b. Now how to do it? We know that the potential of a uniformly charged sphere, or because of this at a given point r from the center of this sphere, is q r over 4 pi epsilon naught r, where qr is the charge enclosed, 4 by 3 pi r cube into rho. Now let us say I bring another dqr charge from infinity on this sphere and I uniformly apply it on the surface of the sphere. So it will be 4 pi r square dr into rho. So this will be the charge which I will apply uniformly on the surface. It will increase the radius by dr. So this will be the volume, dv volume. So dqr is equal to dv into rho. This is the volume, d small v. So this is the small charge which I will bring from infinity. So the work done to bring this charge will be this small charge into the potential which is already there because of the already present charges. Okay, so on putting the value, I can have 4 by 4 pi r square dr into rho into qr. What is qr? Qr is 4 by 3 pi r cube into rho over 4 pi epsilon naught r. So dwr will be written as 4 pi got cancelled out, 1 r got cancelled out. So I can write it as rho square 4 pi over epsilon naught, dr will be here and r 4, and again this 3 will be here. So this is the work done which will be required to be done when I bring this small charge from infinity. So the total work done to put this whole sphere together will be dwr when this radius changes from 0 to b. So it will be 4 pi by 3 epsilon naught rho square r 5 over 5 0 to b, or it will give me 4 pi rho square over 15 epsilon naught into b raised to power 5. So this will be the total energy of this sphere with uniform charge density of rho. Now let us further try to take our expression of potential energy which we found half of Qk Vk, where k was varying from 1 to the total number of charges. Now we want to modify this equation for a case when the charge, instead of being point charges, is uniformly spread. Okay, so how to do that? So this Qk can be approximated as rho dV. Like this is a small charge Qk, and this is enclosed in a volume dV with the uniform volume charge density rho. So this Qk is equivalent to rho dV. So you see that electrical work or the energy stored will be half of rho delta V or dV, V which is already present because of already present charges. Or I will change this summation sign now to integral sign. Will be rho, the potential due to already present charges there, into dV dash. Now I am using prime so that I don't confuse with the source and the field point over the volume full V dash. And this is the potential, this is volume. So don't get confused between various V letters or symbols. So you see in continuous charge distribution, the potential energy is given by half of rho V dV dash over volume V dash, and for point charges it is given as half of Qk Vk, where k is varying from 1 to n, all the point charges. Now I want to point out one big difference between these two kinds of equation. The first equation which we saw for point charges, in that we clearly saw that we were not considering the potential energy which was required to make a point charge. You could have easily seen that what I did, like I brought Q2 charge when already Q1 was present, just work done was equal to Q1 by 4 pi epsilon naught, the potential at 2 because of Q1 into Q2. I did not consider the energy which was required to make this Q1. However, the equation which is for the continuous charge distribution considers that we take the energy of gradually adding all the charges. It means it takes into consideration the energy which is required to form a charge also. That is, it takes all the energy of interaction plus the energy of building the charge. However, this only takes care of the energy because of interaction only. This also includes building the charge plus interaction. So this is a difference between these two definitions, and we will see this difference when we will encounter if any scenario when there is some kind of point charge. You will find that the point charge has to have infinite potential energy to form. So if we calculate from this, we will find the same thing, that this work done will be infinity, because you see the potential energy is Q1 Q2 over 4 pi r. So when this r goes to 0, this will go to infinity, especially if we calculate using this equation, because it is also considering the energy which is required to form the charge. So this difference we should keep in mind while using these two equations. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.